Okay, so now we know that the entropy of a system is directly related to the number of microstates that exist in it. What does that mean? It means that the entropy of the system is related to the number of different ways that the energy can be distributed within that system. And we talked about that when referring to gas particles in a box or gas particles in two closed systems. When you open that system, clearly all the gas particles evenly distribute each other between those two flasks. And that happens because there's just a more even distribution of energy. And that makes sense. But what we need to understand a little bit further is why spontaneous processes go forward. Why are spontaneous processes spontaneous? We discussed at the beginning of class that just because a reaction occurs slowly doesn't mean it's not spontaneous. Just because a reaction or a process occurs rapidly doesn't mean it's spontaneous either. It's the fact that something goes and not the rate that's important. Recall also that we mentioned that the spontaneity of a reaction was related to the entropy of the system, and now we're going to tie those two concepts together. So if you haven't already, pull up the worksheet that I handed out earlier, or that's on the course website, and we're going to go through a couple problems here and help us understand how the entropy of a system relates to its spontaneity. All right, so we'll start with just a quick little lecture, and then we'll get into problem number one. You guys will work together, and we'll come back, make sure we answer it, and so on and so forth through the questions. All right, so first, in order to really understand what makes a process spontaneous or not, we have to understand the second law of thermodynamics. Right, and that second law of thermodynamics states that for any spontaneous process, the entropy of the universe, meaning the system and the surroundings, is positive. So entropy is always increasing. So in mathematical terms, what does that mean? The delta S of the universe is equal to the sum of the delta S for the system and the surroundings. And again, that value is always positive for a spontaneous process. Right? So this is where we're going to get into the activity. Consider two metal bars. I've drawn them red and blue for a reason. The red bar is a hot bar. It's somewhere, let's just say it's around 60 degrees C. And the blue one is a cold bar. Let's say it's around 20 degrees C. Now what happens as these two metal bars touch each other and come together? And for the sake of simplicity, let's pretend that there is nothing else around it. It's in a vacuum. So there's no heat lost to the air. Right? It's in a complete vacuum, totally insulated from everything else. So the universe is the two bars. Right? And we will set and denote the blue, the cold bar, as the system, and the red bar as the surroundings. Hopefully, you guys all intuitively can grasp that those two bars will eventually become the same temperature, and the heat will be evenly distributed throughout both metal bars. Right? That is a spontaneous process. I don't think any of us expect, when you combine a hot bar and a cold bar, the hot bar to get harder and the cold bar to get colder. In fact, it makes intuitive sense that they both equilibrate and come to the same temperature. Now, how can we understand this with regards to the second law of thermodynamics and the entropy of the system? Right? So that comes to our first question on your workbook. Think about this idea. For this process, is the delta S for the surroundings greater than 0 less than 0 or equal to 0. And the same thing for the system. Take some time, work it out yourself, talk to your lab partners, and then we'll go through the answer. I'll walk around and help it with any other questions you have. All right, we're going to hold this answer for now, actually. I want you to keep your answers in mind, and we're going to go through to the next one, and we're going to come back to it, revisit it, when we get to question 3. But first, let's consider the system entropically and see how things are working out. All right, so again, to simplify matters, let's take just a small portion of each bar, and let's consider each one as 4 metal atoms. Right, it's an oversimplification what's going on, but it does help to understand exactly what's going on. Right? So if we consider the hot bar, 4 metal atoms, that bar is hot, and so there is a higher amount of energy in the hot system than in the hot surroundings than there are in the system. Right? So we'll signify that amount of energy by these little bars around each atom. And that helps to make sense because these molecules, these atoms, are vibrating when they're hotter more than when they're colder. So we'll assume that this has a total of 1, 2, 3, 4, 5 quanta of energy, 5 levels of energy. Again, an oversimplification, but it should help to understand what's going on. So the hot system has 5 energy levels available to it. And the cold system, because it's colder, has less, just 1 quanta of energy available to it. So the question is, how many different ways can we distribute the energy in each of these systems? Right? So for the cold, what's the number of microstates? And for the hot, what is the number of microstates? Right? And I think to help you understand how to do this calculation, not something that you need to have memorized, but there's a simple formula, not so simple formula, that should help to understand this. For any given system, the number of microstates, which we'll signify as omega, is equal to so n, the number of quanta of energy, the amount of energy in the system, plus the number of atoms in the system, minus 1, factorial, divided by the energy in the system times the number of atoms, minus 1. So in this instance, we have, we'll just give you the setup. 1, 2, 3, 4, 5, plus 4, minus 1, factorial over 5 factorial times 3 factorial. All right, now solve both and give me the number of microstates for each system. Pause, talk with your lab partner, figure out the number of microstates, and we'll pick up from there. All right, so hopefully by now we've figured out that the number of microstates for this system is 4. And that's easier than actually doing this equation because we can put this 1 quanta of energy only on each atom and there's no other way to distribute that energy. For the hot system, 56. You can do the math, and we need to have some sort of formula to figure this out because it's a lot harder to do all the permutations and make sure you don't miss one. Right? So, but there are 56 based on this equation. All right? So, this makes sense. There's more entropy in the hot system than the cold system. The molecules that move around, there's more distributable energy, and there are more possible distribution states for that energy for this system. So, let's move on to the next question and figure out, well, how does the entropy change